So now this should actually switch. I'm turning it off and on again. No? There we go. I pressed the wrong button actually. So just a quick introduction. My name is René. I do C++ since like roughly 10 years and work at Nexenio for like 3.5 years now. Let's just jump right in. So first of all, why do we need these asynchronous workflows? What are they after all? And is the SDL providing us with some building blocks for those already? So let's have a look. What do we actually want to solve? Well, the application already Matthias talked about is a desktop client for a cloud storage synchronization software. So basically it is an end-user application with a graphical user interface. It will need to deal with some program state like every other program probably in the world. It has some business logic, and since we are synchronizing files, we will need to deal with some network I/O, we will need to deal with disk I/O, and also as an end-to-end encrypted solution, also some compute. So all of these things we want to do without blocking the GUI thread. This is pretty much the issue we want to solve here. It's not a new issue, of course, like pretty much every graphical user interface application will probably have the same problem. I want to show you how we solved it. So first of all, what is a GUI thread or event loop in Qt's sort of sense? Well, an event loop is basically what Qt uses to interact with the GUI. So you have an event queue, and this queue contains events that are, for example, the mouse just moved, or the mouse was clicked, or a button was pressed, or you name it, everything. And you have a single-threaded loop that basically just picks the first event from the queue, handles it, which might or might not result in new events for the queue, and this is an ongoing process and basically renders your graphical user interface and deals with all the things that your graphical user interface is getting from the user. That for a programmer is easy to understand. It doesn't have any concurrency, so we don't need to deal with synchronization for this and so on and so forth. The big problem is once this event handler actually runs a long-running process, for example, opens a file and reads it, or talks to the server and the backend team didn't do a good job and doesn't respond for 2 seconds, your GUI is unresponsive and you see those little guys. Depending on the platform you are on, it's one or the other. So the solution that every book will tell you, well, just offload your compute or your I/O to a worker thread. What could be harder, right? Well, what we wanted to do is not just spawn a thread and deal with all the threading and synchronization logic ourselves, but to have a more or less simple and intuitive API to do this. We wanted this API to be data flow driven, so instead of dealing with the synchronization and the thread handling and everything ourselves, we wanted to basically just type out what our data flow asynchronously in the background should do. And in the best case, we wanted to have one asynchronous concept for both I/O and long-running computation. So let's have a look what C++ already offers us. We have STD threads in C++11, amazing. It is basically giving us a very thin layer on top of the platform-provided thread APIs. That's something, but it's really only that. So even if you return a value from the STD thread lambda you use to spawn a second operating system thread, this value is ignored. So the only way you can interact from this thread with other threads, for example, the GUI thread in your application, is to use side effects. And side effects in this regard is a direct way to synchronization problems, to deadlocks, to races. I'm sure all of us been there. There is another way, and it's STD async. That's a bit better because it is an abstraction on top of the low-level STD thread API. It doesn't just eat the value you're returning from it, but it returns it via an std future. Now, can I assume that everybody knows how an std future works? I take this as a maybe. So basically, an std future allows an asynchronous process to return something to the caller immediately, but it doesn't necessarily contain the result of the asynchronous operation already. So you as a caller, you don't block, but you get a handle which you can use to later obtain the data that was asynchronously computed for you. So the C++ STL gives you this sort of future functionality, but the problem is when you are the GUI thread and you use this std async, there is no way of telling whether the future you received at some point is actually already finished and contains a value or not. So at some point, you're just gonna need to make the plunge and call task get, which will potentially block your GUI thread. So that's also not really a solution. So it turns out that, well, C++ 11 and up to 17 doesn't really give you something to express something like an and-then relationship. Like a simple callback is not really in there. So how do we solve that? Well, what the answer for many of these things is called continuations. And the continuation was actually, I think it was even discussed to put it into C++ and concurrent CTS, but eventually was never put in there. So we need to look somewhere else. Anyway, what is this? Say we want to read a file because we want to sync it into our cloud storage provider, and it is very personal to us, so we don't want to have it read by everybody. We call read file. Read file is an asynchronous function that returns immediately. It doesn't block, but does the computation in the background in another thread. And it returns a task. Now a task is pretty much the same like a future, but it lets you do one more thing. And that is you can call .then on that task, which basically attaches a callback. Once the task is done, this callback is executed, and it gets passed the value of the result of the asynchronous operation. In our case, it is the buffer containing the content of our love letter. So you could go ahead and take this buffer and throw it into an encrypt function that encrypts it securely. And this encrypt function is asynchronous as well, so it returns another task, and you can start to chain those continuations together to build a sort of workflow. What you're actually doing is you spell out for the computer with a bit of boilerplate for sure, but still, what you want to do asynchronously, step by step, kind of like a small execution plan. First do this, then that. And the task is, since it is close to a future in semantics, it also has a get function, which again blocks. So that's not what we want to use. But in order to call back into the GUI to tell the graphical user interface, hey, we were done with uploading, we just, I guess you guess it, just add another continuation that reports back asynchronously into Qt's event queue and basically just puts an event into that queue, which then can be picked up. So the last continuation basically says Qt's emit file upload finished and gives the result back. So there are three main takeaways here because I think that is a bit technical. First, a task is just like a future, a handle for an asynchronously provided result, but at the same time entails an execution plan for how to get to that result. Second, continuations can be chained. So you can, continuations are just simple callbacks that are called as soon as the asynchronous operation in the task is finished. And third, these continuations can be changed into somewhat workflows. So let's have a look how our application uses this. First, we have the event loop of Qt that we don't want to block. And instead of just doing something in the event handler that is long running, we now just schedule one of those tasks. And this task actually entails more than just handle, but also the whole execution plan that is supposed to be asynchronously executed. And after this is set up, which is super quick, basically just a few small non-blocking function calls. It returns the task back to the event queue, and the event queue can continue doing its job, show a spinner, whatever. In the background, we have a thread pool, and this thread pool is then used to schedule all of those tasks. In idle worker threads, at some point this will finish. It will have this report result tasks, which talks back to the GUI thread, and we're happy. We never blocked our GUI thread, but we still accomplished our task asynchronously. Now, obviously, we didn't implement all of this ourselves, but it is based on a Microsoft technology, namely the Parallel Patterns library, which provides you with this task parallelism framework, and at the same time provides other things like parallel algorithms, containers, and everything. But you might think, yeah, well, that's just Windows, but we talked about Linux and macOS and how hard it is to sync in between them. So Microsoft was gladly provides a cross-platform version of this called PPLX for cross-platform that only takes the task parallelism part, so no fancy parallel algorithms, and ports it to all platforms we care about. Plus, it under the hood actually uses the thread pool implementations of the specific platforms. So for macOS, it would use Grand Central Dispatch under the hood, and for Windows, I think the Windows concurrency runtime. So it is actually properly efficient and really well maintained and useful. Plus, the same thing, the same library comes with something like the C++ REST SDK that gives us HTTP client server over this task model, and also file system I/O, also based on the task model. So that's actually really nice for us because it solves the problem that we had, that we want to have everything under one concept. So, but the thing is, these workflows, you saw it, they add quite a bit of boilerplate. So we needed to come up with something to make this actually scale, and actually make it scale to an extent that pretty much all our business logic is implemented just like that. So how do we structure our workflows? Like as a side note, if you have any questions, please don't hesitate to interrupt me.
You said that you get like a handle to this task, but do you store it somewhere since you always and only for then, even for updating the GUI? You never forget, as far as I've understood you.
That is our goal, to never actually block. So we should never call get. And thank you for the questions. I'm going to answer it right on this slide.
Okay. Question to this reminds me a lot of JavaScript promises.
Yeah.
And there you can also, instead of then, you can call catch and finally, and exceptions are forwarded for these tasks. Do you have something like that?
That is exactly the same thing here. So basically, if one of those continuations throws, I left the error handling out of the talks to keep it short, but anyway, I give it to you. If one of those continuations throws, the library basically catches the exception if you don't do it yourself, stores it in the task, and then if you eventually call get on the task, you get the exception rethrown and you can handle it. Anyway, so let's go back to this tiny workflow that we talked about, and I can imagine that each of those steps are actually complicated enough to look deeper into them. So if we want to read a file, we might need to open it, which might already be an asynchronous thing. Then we might want to read it blockwise because it is big, and then we want to aggregate it into one buffer. Let's not talk about streaming and everything here to keep it simple. And the result of this aggregation is then passed into encrypt, which on its own is fairly complex. It might even need to talk to the network. It might need to generate some keying material, encrypt it, and so on and so forth. And the same is true for uploading. So all of these steps are in its own a small asynchronous operation that are chained together by these continuations. And now to your question, at some point we want to talk back to the graphical user interface, And we do this with this extra reporting task that is attached in the code of the graphical user interface. Basically, in the event handler of the button press, I say, okay, fire up all of this, and then eventually, with a final then, give me the result. This frees us from the get we would otherwise need to make in the GUI thread. And I think you see where I'm getting here. Those are actually all individual workflows. So we can implement those independently. We can test those or best case want to test them independently. They might even reside in different code units or libraries or whatever. And how do we do that? Well, let's look into one of them. Let's look into the workflow push file, which is kind of the orchestrator for the other workflows. And it has a very simple interface, as you might guess. Basically, it just is a freestanding function push file that is provided a path and it returns a task. The implementation in a C++ file, so there we have the advantage of putting things into independent compile units here. So basically, if we want to implement on one of those workflows, we don't need to recompile everything because we are doing crazy template magic. So the implementation of this is actually fairly easy to test and develop. But there is one issue in the code regarding all of the the software engineering of this thing, and it's tight coupling. We would call statically into the other workflows, and we do not really want that, because otherwise testing this would be a nightmare, because we couldn't test each and every workflow in isolation, because it would always call into its friends. So what we have implemented is a workflow decorator, which it basically just is a thin facade for all our workflows, and introduces like a virtual function call in between that we in a testing scenario we could just mock the function calls, and instead of actually calling read file to actually read a file from disk, the mocking framework could just throw back some test data at us. And on top of this function for the workflow decorator that it allows us to mock things, it also allows us to do dependency injection. So that is the other big advantage of this whole workflow thing. Each workflow might have further dependencies. Like, for example, an encrypt operation might not only get the buffer to encrypt, but it also needs to get a random number generator. This is one of our dependency objects. And the dependency object, in our sense, is usually singleton objects. So they are not really singleton in the programming sort of fashion, but they exist only once in our program. And usually those dependency objects, they retain some program state or provide a service. And also they are pretty much the only objects in the system where we really explicitly need to care about thread safety. Because like the random number generator exists only once in the system, but it might be used by different workflows concurrently at the same time, and that might lead to threading issues. But dealing with this is fairly easy. Usually we basically just do a mutex around the public interfaces of those objects, and that's already it. So how does this now look like in the code? Like, say we want to look at the encrypt sub workflow and how to call it from the orchestrating push file. So the encrypt actually has this more complex API. So it needs a random number generator, it needs a REST API to talk to our backend service, and it actually needs the workflow decorator too. So the workflow decorator in itself is also one of our dependencies because it offers the service of calling other workflows. And the facade function, the wrapper function in the workflow decorator for this encrypt function is publicly just what we would expect, which just takes the buffer that is supposed to be encrypted and then internally calls the actual workflow and injects all the requirements that this workflow might need. Now, for simplicity, I just spelled that out here. What actually happens is some template meta programming that figures out based on the function declaration, what workflows this, what dependencies this workflow is actually needing, and stuffs them in there. So I don't actually need to go back to this wrapper if I add a definition up here. I don't see any raised hands.
One question. Is there any reason, clear reason, why workflow decorator is the base of a virtual hierarchy and not the base of a templated hierarchy?
Yes. Well, first of all, never really thought about that. By making it virtual, it is easier for most mocking frameworks to deal with it, because then you can just override the workflow decorator with your mocked workflow decorator and override these calls. Obviously, you could also do this with a template, but then you would need to do it at compile time. And the performance gain you would get from this templating game is probably negligible, because we're talking about small asynchronous operations that need to be scheduled to work threads and everything. So I would guess that you wouldn't gain enough to go all that way. But I might be wrong, and we never tried. So now, how does this all play together? Let's zoom out and look at the whole program doing its thing to upload a file. So the user decided to upload their love letter and calls from of course via a button, right? But the button calls into the workflow decorator and says, please push that file into our cloud storage. And the workflow push file, as we saw, is just an orchestrator. Sorry, coming back to your question actually again, the second thing this graphical user interface needs to do is to add a final continuation, basically, to deal with the result of pushing a file. That is all that the graphical user interface code needs to know. There's one tiny little detail here. It's this inQt wrapper. We also have that in our code, and it basically takes the lambda that you pass in and wraps it into another lambda that deals with taking the result and moving it into the GUI thread already. So, so to simplify Qt's life. Otherwise, we would need to, like, Qt doesn't really like it to emit signals from worker threads in layman's terms. So we need to have this little extra step there to first jump back into the GUI thread. So the workflow decorator, now having the task of pushing a file, realizes, okay, push file needs me to call other workflows, injects that behind the scenes, and then calls the actual workflow. This now starts executing. The first thing it does is, okay, well, let's call this up workflow read file. And read file doesn't have any dependencies, so it just reads the file from disk, comes back with the result, and now workflow push file retained the file content. Next step, we call into encrypt. Again, right, as I explained, we only pass the file content buffer, nothing else. And the workflow decorator does the heavy lifting behind the scenes, injects all the dependencies, and comes back eventually with now an encrypted byte buffer that is stored in the local state of this push file workflow. And I guess you know where I'm getting at. Well, we call the upload, which just needs the API as a dependency, and eventually comes back with some upload result, whatever that might be, which is then reported back to the graphical user interface, and it can be like, hey, I uploaded your file. So that is pretty much how we orchestrate these continuation-based asynchronous workflows. And let me just quickly wrap up. We found that std future and std async, and even more so std thread provided by C++ up to 17, doesn't really solve the problem for the concurrency and asynchronous operation problem for a real-world application. You actually need to put in more machinery. The continuation style with these tasks has a bit of a bad reputation in the community, I felt, while preparing that talk, because you find other talks at CPPCon and other places where they're like, yeah, it's super hard to read and everything. But we found it to be actually fairly flexible and really well suited for our job. So,
just out of interest, why would they say that they find tasks unreadable? What's the alternative those people would use that they find more readable?
maybe STD, maybe Boost ASIO. I'm not sure if you really want to go there.
I mean, I think it's pretty readable. Like all the web technologies, like all the languages out there using seem like syntax, like this continuation language called promises. I don't see a reason why not to use it.
No, I find it readable.
Maybe I find it unreadable. Of course, it is okay. It's not completely unreadable. But if you go back one slide or two slides, here, the push file. I mean, it leaks everywhere, right? And push file just wants to read file, encrypt, and upload. But it also has to deal with tasks. And in principle, push file just wants to do three things in sequence. Where normally you would just write read file, semicolon, encrypt, semicolon, upload. Now we have the then and all this.
It definitely adds boilerplate.
Syntax, which doesn't help you there because you're not doing asynchronous stuff in a way. You
can't parallelize it.
Yes, exactly.
I know.
I mean, you could do it all in one task. It doesn't help you that you schedule stuff.
Yeah, the question is if
okay, now
practical sense and splitting it that small. So you could just have one background task or two at most.
Those three can be everything that's dark gray is basically one function.
Now I know where you're getting it. The thing is, if you do this and then you have a lot of workload, at some point you're running out of worker threads because they're all waiting for some I/O. You know, like yes, we do, but the thread pool has, I don't know, 50 threads. Maybe it also scales up if the threads run out. But you know, like if you have this as one function and then everything in there is blocking, that's fine. You don't block your GUI thread. But if you have 50 of those functions concurrently, at some point you have 50 blocked worker threads, all waiting for your disk.
Yeah, but isn't the idea of a thread pool that you have a budget for threads, let's say 10 or whatever?
Yeah, it is.
And then you have a waiting queue for tasks waiting to be executed. So you don't have hundreds of threads, then they're just executed in series somehow.
That's true, but still you, like say you have 10 tasks that all need to run like some long-running computation and they block your whole worker threads and you ran out of worker threads. Now the 11th task comes and wants to upload a file and this was spawned by the user and you want to have an immediate feedback, but it needs to now stand in line and wait for one of those long-running tasks to be finished, while with these finer-grained asynchronous workflows, you would very quickly progress with all of your tasks, not only with the 10 that your thread queue allows.
One question. I'm not worried about the real process of when everything goes right.
Mm-hmm.
I'm worried about the process of when something goes wrong.
Mm-hmm.
I mean, if read file fails, it must somehow give some kind of result to the report file that is an error that should be compatible with all the rest. So
Yes.
that looks like putting a lot of limitations on how you can process any error in this composed flow.
Actually, not really. Let me find my mouse on the screen and then I show you the slide with all the code, where I had all the code in one slide. Where is it? Here. Animations and things, you know. Come on. Did I really just go too far? So imagine, let's say encrypt would throw for some reason. And now I will go into more detail than I actually planned to, but if you have a continuation that just takes the type of the result of the previous continuation, this thing will be skipped as soon as this thing throws an exception. So encrypt throws, I don't know, key too short exception. This thing will never execute, but this thing will, because it doesn't take the upload result just verbatim, but it takes the task of the upload result. And as I mentioned briefly via another question earlier, if this thing throws, the exception is encapsulated in the task and then rethrown here. So because we do a continuation here that takes a task rather than just the value, we get that task once it is done. So at this point it is fine to call get because we won't block, otherwise we wouldn't have been in this continuation. Here it's getting technical, I'm sure.
Yeah, anyhow, I see there, it's good. Yeah, I see there that you are limiting the kind of ways of reporting the exception. You should, that's a question only. In the catch, should it have a simple throw? Rethrow the current exception to avoid limiting the kind of errors that can be reported?
You can throw whatever exception you want.
So that's something that you write on the task. It's nothing that is pre-created on the task. The catch part.
Like here?
Yeah, what I mean is this is something that you write for the task. So it's
Yeah.
your option to do anything with it.
Yeah.
It's not something that is pre-written or pre-created on this task.
Yeah, exactly. This is what basically the code in our graphical user interface would do. It would call it would call push file and then task upload result, get the result. If everything is fine, we just report back to the graphical user interface, to the event queue and show the check mark. And if something on the way broke, we would get this exception here again. And then we could add catch as much as we want and handle the exceptions that were.
Or even avoid the try itself and let it through.
Yes, that is actually prohibited by the framework, because what would happen in this case, it would throw out of this exception, out of this continuation, would be caught by the framework, by the task framework again, and the task framework would assume that at some point you observe this continuation by calling get on not this task, but that task. And if you fail to do so and this task gets destructed later, it would actually throw at this point and crash your program. Okay.
Just a little side note. Doing some JavaScript. What you're doing here is like avoid the callback hell. Usually you have like callbacks and avoid the callback hell if it's really messy. And then what in JavaScript happens, okay, we avoided the callback hell, we are now in the then hell.
Yeah.
So, but that's already, to my opinion, quite readable. But what JavaScript did, they introduced in ECMAScript 8, I think, await.
Thank you for asking.
No brackets, no like, it's just like await function call or await variable equals the function, and then you can go sequentially through all your tasks. I don't know if C++ or your framework here is doing that, but
not yet, because C++.
It's not far away, and then when you combine it with ranges and get fancy, then you have one function and call it to everything in the world. It's like really beautiful.
One more year, C++ 20 will have it.
We'll have it, yeah.
Well, at least to a certain extent. We're looking forward to it.
Yeah, JavaScript did it. So.
Yeah.
So I have a question about this include function.
Mm-hmm.
It looks nice for reporting one result back to Qt, but what if you have something like a progress bar where you need to continuously report back to Qt?
Mm-hmm. What we are doing there is we have a support object, basically a progress, how would I call it? We just call it progress, but like a kind of like a progress tracker that we put in all the way at the top as a second handle that can be updated while running the asynchronous workflow. So this thing the workflow itself needs to aid this process. But that proved to work fairly well. But of course, this progress thing then again needs to deal with the thread synchronization because it cross-talks over to the GUI thread. So unfortunately, this thing can only return one result. It's not like a reactive sort of stream where you could, throw a whole stream onto the asynchronous task.
One question. So you mentioned that you write your API in Qt. So why not evaluating to use Qt threading, for example, Qt future, and so on? They also have callbacks and all that stuff, so it should probably be possible to do something similar.
Most likely it does. To be honest, we didn't really look into this one because we were not quite happy with Qt's networking layer. Like the Q network access manager really didn't serve us well. So we looked for something else to do networking, and we came across this CPP REST SDK, which stuck on. And since it brought all of this task handling with it, we basically jumped over to that one. But yeah, could be that Q Future has this continuation work as well. Like actually, there are several libraries that implement that for C++. Yes?
Would you say that these Microsoft frameworks have some limitations, be it a REST part or this task API? Something that you don't like or hate about it?
The thing I hate most about it is that they are not really maintaining that anymore. It is they have it on GitHub, and they accept pull requests, and it is community driven, so it's not that it completely died, but Microsoft is not really putting a lot of effort into this anymore, which so far didn't bite us that much because it's fairly feature complete, but in the future we might actually have a problem.
Why are they not doing it? So they do something else?
I'm not sure. Like we opened an issue at one point and we're like, do you still use that? And they're like, yes, we are still using it in Azure Cloud and we're still using it here and there. So it is heavily used, but not much invested into at the moment. So to the point that we actually started maintaining some of the things in there. And like to add that, it was surprising. The code of this is like, since we started to contribute to it, we looked quite deep into it. The code of it is actually really nice to read, really nice to extend, all the way to the extent that at some point we forked the project, and we are actually using our own TLS library in there. So we actually ripped out their network stack and replaced it by our own. And that was fairly easily doable. So let me just come back to the coroutines thing as a final remark. So do we look forward to coroutines? Absolutely. This is what we saw all the time with coroutines. It would look somewhat like this. And it would have pretty much the same semantics in a much better readable fashion. Please don't quote me on the details on the syntax. I actually never tried it because I wanted to try it the other day, and I realized that my compiler wasn't yet new enough. And then I realized that this is shiny and everywhere on the box, but actually you need to implement quite a bit of boilerplate because the STL didn't catch up to this coroutines thing yet. But eventually C++ will get there. So, thank you very much.